Now let's take that previous example, but add an applied force to it. So we have our box sitting on the floor, but now imagine that you are pushing or pulling on it at some angle. Okay, you're applying a force to the box. Maybe you're pulling on it with a rope or something, or just pushing with your hands. And you're pushing forward and slightly upward. So let's analyze this using our Newton's second law problem solving procedure. There's our sketch. Now let's draw the free body diagram. The object of interest is the box. A good coordinate system is still regular old vertical, horizontal, x, y. Let me make this a little bit bigger. There's our object of interest at the origin. Now we'll identify the forces. As usual, there's gravity of the earth on the box. There's a normal force of the ground on the box. And additionally, there is this applied force. Let's say that's caused by U pushing on the box. Y for U, B for box. And that's happening at this angle theta. 3 forces. And notice that the normal force and gravity force line up with one of the coordinate axes. They line up with the y-axis. But this additional applied force of U on the box doesn't line up. So yes, we have to do some trigonometry and get our vector components. So I'll draw a little picture over here. F, Y, B. Theta, here's F, X, here's F, Y. Right, you can imagine this right triangle here with the X and Y components. X is adjacent, so it gets cosine. Y is opposite, so it gets sine. All right, so we've expressed all of our vectors in component form, and now we can write down our Newton's second law equations. So let's do Newton's second law in the x direction. There's only one vector component along x. It's just this one, just that applied force along x. So we just have F of U pushing on the box in that x direction, which means that the box is accelerating with magnitude F cosine theta over m. We can do Newton's second law in the y direction. And there are 3 forces in the y direction. There's normal, that's positive. There's the y component of that applied force. And gravity is going down, so we give that one a minus sign. And we'll assume that this thing is not moving in the y direction. It's not accelerating up or down. So the right-hand side of the equation is 0. 0 y acceleration. And now we have some relationship between these three forces, and maybe we want to solve for the normal force in terms of the other two. So the normal force would be W minus F sine theta, or you could write mg minus F sine theta. And you notice that this time the normal force is less than it was in the previous example. In the previous example, without this force here, normal force equaled the weight. It equaled the gravity force, which I told you was kind of a coincidence. This time the normal force is less. Let's think about that. You're directing this applied force slightly upward, so it's like you're lifting the box a little bit. That means the ground doesn't have to apply as much upward force to keep the box from falling. So the normal force the ground applies is reduced by the amount of lift that you're giving it.